Hi everyone, today is fun maths. 2 plus 2 equals to 5. Oh, what's this again? So today we are talking about inertia. What is inertia?
Hi everyone, today we will be solving many questions on simple harmonic motion, specifically mass spring system. Now, if you haven't watched my video on mass spring system where we derive and explain many things under it, we should please go and watch it. Now, this is the first question that we'll be tackling. If you can solve it, you can pause the video and give it a now. The first question is, which is resting heartbeat is 16 beats per minute. While he's doing some house chores, it rises to 80 beats per minute. A determine for both cases the period of the motion, the frequency of the motion is the beating of which is at simple harmonic or is it periodic. Now, whenever you want to tackle any questions in physics, we know that it's either we write out our parameters or we draw out the diagram to know what they are talking about, or both in some cases. Draw out the diagram and write out the parameters so that you can understand and see the clear picture of what they are talking about. Here, we are not going to be drawing at speed since we have known what they are talking about. So we are just going to start writing out our parameters. And here they said the which is heartbeat is 60 beats per minute, and we know that um for us to have beats per minute is talking about frequency, because I said in my last that video that frequency is number of oscillation over time, and time should be in seconds. The SI unit of time is seconds. Why number of oscillation does not have any unit. Therefore, we say that the unit of frequency is per seconds, or we say it is measured in hertz. Now, here we are given time to be in minutes, so we have to convert that. So let's write the parameters. We can break it down in saying that they gave us number of oscillation to be 60 bits. In how many minutes? Time to be in just 1 minute, and 1 minute is equivalent to 60 seconds. So let's note that 1 minute is equivalent to 60 seconds. And they said while he's doing some house chores, it rises to 80 beats per minute. Now, the second beat given to us is 80. So we have 80 beats, and the minute does not change. 1 minute, 80 beats per 1 minute, which is also 60 seconds. Now, let's start tackling the question. The first question says, determine the period of the complex motion. Now, the period T1, let me do it here. The period T1, because for the both cases, for case 1, which is for this, and for case 2, which is for this. So those are the two cases we are doing it for. First period is equals to time over number of oscillation. Remember this, I explained this in my last video. Time over number of oscillation, and time is 1 second, which is 1 minute, which is 60 seconds, over number of oscillation, which is 60 beats, and by the time we divide it we have 1 second. So our period for the first one is 1 second. Our period for the second case, that is T2 over N2, will be 80 over 60, and by the time you punch it inside your calculator, you are going to get 1.33 3 seconds. Now this is our period. Now moving to the second question, they said we should find our frequency, and we know that our frequency is just 1 over period, and we can just do it for the first one, that the first frequency over the equals to 1 over first period equals to 1 over 1, since our first period is 1, so it's 1 over 1, which is also 1 hertz. So that's the frequency. And the second frequency is 1 over t2, which is 1 over 1.33 seconds, which is going to give us 0.75 hertz. So that's how you tackle this type of question. And is the beating of Uche's heart simple harmonic motion? Now, I told you something about simple harmonic motion, that simple harmonic motion must have a restoring force. And since it is heartbeat, it's something that occurs naturally. It doesn't have a restoring force. Therefore, is not a simple harmonic motion because it doesn't have any restoring force. But is the beating of Uche's heart periodic? Yes, it is periodic because it occurs at regular interval, and this is what I even use as my example when we were discussing periodic motion in my last class. So let's move to the second question. This is the second question. Consider the periodic motion of a body if acceleration equals to -3 centimeter per second square when x equals to 2.5 centimeter and -4.3 centimeters per second squared when x equals to 3 centimeter. Then the motion is a simple harmonic motion, B not a simple harmonic motion. Now let's investigate if this motion is a simple harmonic motion. Now, the first thing you are doing is to list out your parameters. We were given acceleration and we were given distance. I think those are the only things given to us. So we have acceleration being given to us, the first acceleration being given to us as -17 per second square, and my displacement 2.5 centimeter, the first one. And for the second one also, my second acceleration is -4.3 centimeter per second squared, and my displacement being 3 centimeter. Now we are to determine if it is simple harmonic motion or not. And remember from my last video I said acceleration is directly proportional to the negative displacement, as we derived earlier. Now for this, now I can just introduce constant, since I cannot solve with this constant proportionality. I will have to change this to equals to, and whenever I'm changing it to equals to, I must introduce a constant. Say constant W. I can, okay, don't let me use W, let me use constant beta. Let me use beta as my constant beta x, something like this. And here I can divide both sides by x to make constant be on a side. So I can say a over x is equals to beta, and beta is constant, remember. And whenever we have any function that is equals to beta, it means this function can repeat itself. For instance, I can have a1 over x1, it must be equals to a2 over x2, which must be equals to a3 over x3, which is equals to till an over xn. So this is how we form many formulas with constants. So it must be equals to each other. And let's now investigate this function. We have a1 over x1. Since we are having only two functions here, a1 and a2, x1 and x2, we are just going to consider only just these first two parts, which is a1 over x1 equals to a2 over x2, and a1 is negative 3 over x1 is 2.5, which is equals to negative 4.3 over 3. Now, mind you, I did not convert the centimeter to meter because meter is the SI unit, because this x also is in centimeter. So I don't need to convert, because both of them is going to cancel out. That's why I don't need to convert. Now, let's come back to the equation. Negative 3 over 2.5. What do we have? We have negative 1.2. Let's now check the second side. Negative 4.3 over 3. We have negative 1.43. And we can see that these two are not equal. Since these two are not equal, it means the answer is not, the periodic motion is not simple harmonic motion. If it is simple harmonic motion, this must be equals to this. Similar question to the one we just solved. You can just pause and determine if it is a simple harmonic motion or it is not a simple harmonic motion. Now let's move ahead and solve it. Let's list all our parameters as we do. They said consider the periodic motion of a body if the first acceleration given to us is negative 3 centimeter per second squared, and the first displacement is 2.5 centimeter. Okay. The second acceleration given to us is negative 3.6 centimeter squared, and the second displacement is 3 centimeter. Now we have to determine if it is simple harmonic motion or not, and we know that a1 over x1 is equals to a2 over x2. Now let's check if this is correct. So we have minus 3 over my x1 is 2.5, which is equals to my a2 is negative 3.6, and my x2 is 3. And then if I should punch this inside calculator, 3 divided by 2.5, I'm going to get negative 1.2. And if I should punch the second one also in the calculator, I get negative 1.2. And we can see that both of them, the left hand side and the right hand side, are equal. Then this is a simple harmonic motion. So that's how we just determine a simple harmonic motion through what is being given to us. Let's move to the next question. Consider the periodic motion of a body if acceleration is negative 3 centimeter when x equals to 2.5 centimeter, and negative 3.6 centimeter when x equals to 3 centimeter. Then its period of oscillation is. Now this looks like what we just proved earlier, that it is simple harmonic motion, whereby we knew our we compared our acceleration, the ratio of acceleration to displacement. Now here we were asked to find the period. Now how do we do that? Firstly, let's list all our parameters, and we are looking for the period t. You can go ahead and solve this question if you can try it. Let's now continue. Let's solve this question. Now we were given acceleration and we were given this, and we are looking for period. And remember, the formula for your period is either t over n, or 1 over f, or 2 pi square root of m over k. And if you should look at this question very well, none of it is looking the same. The parameters given to us is not looking the same with it. So what you do is that from what was being given, you will check what this that was given can produce to give you something similar to this. That's how we check. And remember the force that we said that it's directly proportional to our displacement, and we said it's obey Hooke's law, which is equals to negative kx and this F is mass times acceleration, which is equals to negative kx, because we have our x, we have our a. Then I can say that my a is equals to negative k over m x. Then if I should like divide both side by x again, then I will have a over x to be equals to negative k over m. But mind you, in my question, what I need is m over k. I will just flip this, saying x over a is equals to negative m over k. All right. Now my x given to me is 2.5, my a given to me is negative 3, which is equals to negative m over k. This negative can nullify this negative. Then I can say that m over k is equals to, punching this into calculator, 2.5 divided by 3, I have 0.833. Right. Now I can now come back to this formula and plug in my value. Then my t is equals to 2 pi square root of m over k. Now that I have known my value for m over k, I will just plug it in directly, which is 0.833. And by the time I compute this inside calculator, 2 pi times square root of 0.833, I get my period to be 5.74 seconds, and that is actually in option D. So that's how you solve a question like that. You use what was given to you to find what you are looking for. You find a way you can manipulate it to get what you are looking for, and that's the correct answer for that one. This is the next question. It says that consider an object exhibiting simple harmonic motion. If it was released with zero speed at a point away from equilibrium, at what point in the motion does its kinetic energy become one fourth of its original total energy? What they are just talking about is that if you have a body exhibiting simple harmonic motion, like an object attached to a spring, something like this. If this was its initial position and it was being stretched to this point, because they said it was released with a zero velocity, and remember I said at this place velocity is zero, and at the main point velocity is maximum. Please, if you have not watched the video on that, do well to go and check it out. You will learn a lot from it. At a point away from the equilibrium, this is the equilibrium point. Now it was stretched and it was released from this point, that is the distance away from this equilibrium. Now they said at what point on this motion will its kinetic energy become one fourth of its total energy. Now you can just use formula to just um do this. You can do it in different ways, so you will still get the same answer. For instance, they said at what point will the kinetic energy become one fourth of its total energy? And don't forget, your kinetic energy formula is half mv square, and your total energy formula is, sorry, one fourth is half ka squared. Now this one we can change it. Remember, your velocity is equals to omega square root of a square minus x square. We prove this formula there. So we have 1 over 2 m omega square. By the time we square this function, we have omega square a square minus x square equals to 1. If you multiply this 4 and 2 together, you have 1 over 8 k a square. Right. Now we are to like analyze this now. Remember that from omega square equals to um k over m, I can say that my k is equals to m omega square if I should cross multiply. So I can represent this m omega square as my k. So I will say half k a square minus x square equals to 1 over 8 k a square. Okay, now we can see that our half will take half from here to give us 1 over 4. Then our k will take away k. Then we are left with a square minus x square equals to 1 over 4 a squared. Alright, now we can bring this one to this side now. So we have negative x squared on the left hand side, and we have 1 over 4 a squared minus a squared. Now simplifying this, we can have negative x squared equals to LCM is 4. 4 in 4 is 1, and we have x squared minus this one is over 1. 1 in 4 is 4. 4 times this is 4 a squared. Then we can say negative x squared equals to negative 3a squared over 4. And negative cancel negative, we have my x squared to be equals to 3a squared over 4. Then I can say that my x is equals to square root of 3a squared over 4. And square root of a square is a, and square root of um 4 is 2, and root 3 remain the same. So I can say that x is a root 3 over 2 of a. Now we haven't finished our answer because our answer is in terms of amplitude, but they say in terms of cycle. And remember in the video I said one oscillation is equals to 4 amplitude. We can go and watch the video and I explain how that is being done. And one oscillation is one cycle. So I can just represent this oscillation with cycle. That okay, this oscillation I can just represent it with cycle, saying one cycle is equals to 4 amplitude. All right, now let's now relate. Now we want to check how many amplitude, how many cycle and in this amplitude. So I will just say amplitude, I'm going to place under amplitude, which is with 3 over 2 amplitude is equals to what we don't know, so I will call it p cycle. So how many cycle are inside this, then I cross multiply. I will have my 4p equals to, because amplitude we cancel amplitude, so I will say I have my 4p equals to square root of 3 over 2 cycle, right? Then I divide both side by 4. If I should divide both side by 4, I will have my p to be equals to square root of 3 over 8, because 4 we multiply the bottom case, which is 2 cycle. And if I should punch this inside the calculator, I will have 0.217 cycle. And if you should look at the option, there is no option that looks like root 3 over 2 or 0.217. Then the answer is none of the above, because no option correlates with that. And we can use another method in solving this, but what we are just going to do is that we know that our total energy is kinetic energy plus potential energy, and they say that our kinetic energy is actually 1/4 of total energy. So we can just say okay, my total energy is equals to my kinetic energy, which is 1/4 of total energy, plus potential energy. Now potential total energy is half k square, 1/4 of half Ka square plus our potential energy is half Kx square. Then we can now start analyzing everything one after the other. Let's see. We have half Ka square equals to, if I should multiply these two together, we have 1 over 8 Ka square plus 1 over 2 Kx square. And bringing this to the other side, because they are of the same units, K square, we have 1 over 2 Ka square minus 1 over 8 Ka square plus equals to 1 over 2 Kx square. And then I can find the LCM to be 8. How many 2 can I see in 8 is 4. 4 times Ka square, that's 4 Ka square, minus 8 in 8 is 1. 1 times Ka square is Ka square, equals to half Kx square. And 4Ka square minus Ka square will give me 3 Ka square over 8 equals to half Kx square. And since I have something like that, I can start cutting. 2 will cancel 2 here, giving me 4. You can do it manually by cross multiplying and passing all through that place. It's just stress. K cancel K, then I'm left with 3 over 4 at the left hand side, A square, and I am left with only X square. Then if I should take the square root of both sides, I will have square root of 3a square over 4, which is actually the same thing with what we got as a root 3 over 2, because square root of 4 is 2, and you can see it's the same thing with what we got here. And we can also go through the process in converting them to cycle, and we can see that there is no option in the answer. So let's move to the next question. This is another question that is similar to that first question. Now let's pause the video and let's try this one. Okay, now the question says, if it was released with zero velocity at the point away from equilibrium, at what point in the motion does its potential energy become 1/4 of its original total energy? Now here, the potential energy is the one that is 1/4 of total energy. Now, we know that potential energy is half Kx square, and we know that our potential energy, our total energy rather, is half Ka square. Then we can analyze. So we have half Kx square to be equals to 1 over 4 times 1 over 2 is 1 over 8 Ka square. Then 2 we cancel 8, as we say it will give us 4. K we cancel K. Then we have x square at the left hand side, and we have 1 over 4 a square at the right hand side. And our x should be square root of 1 over 4 a square. Now square root of a is a, and square root of a square is a, and square root of 4 is 2. So you can see that our x is actually half of our amplitude. Now if I should go and take halfway through the cycle, I will be very wrong, because this amplitude does not tell us about cycle. It just tell us about the distance, the maximum displacement from the main position, from the equilibrium position. Now let's now find the cycle. Let's find it in terms of cycle. We know that one cycle is equals to 4 amplitude. Now we are looking for how many cycle will a amplitude over 2 be. That's what we are looking for. Then we cross multiply. So we can say we have a over 2 cycle to be equals to 4a p that we are looking for. Remember, is p we are looking for. I will just divide both sides by 4a. 4a over 4a. And 4a cancel 4a, we have p. This a we cancel a, and 4 we multiply 2. So we have 1 over 8 cycle. And the answer is option B. And we can see is different from the option A that we chose before. And that's the answer for that. Let's move to the next question. Okay, this is the next question. Consider an object exhibiting SHM if it is released with zero velocity at a point away from equilibrium. At what position is the motion is its speed maximum? Now, you can pause the video and think of it. Now, this type of question does not need calculation. It just need explanation. For the mass spring system, you know, it's like an object is being attached to it and you give it a force. Like you apply the force to it in dragging it like this. This is the force applied in dragging it this way or compressing it. But let's use dragging it. So it means that you give it a certain displacement, which we call amplitude. Now, just before you release it, at this point, velocity is zero meter per seconds, because at this point you have not released it. That's why they said if it was released with zero speed at a point away from equilibrium, it was released with zero speed at a point away from equilibrium. Remember, this is the equilibrium point, the main point. What we mean by equilibrium point is that when we attach an object to a spring, it has an equilibrium that it attains, but we tend to pull it. As we pull it, then the spring expands and the object gains some distance from here to here. So the distance it gains is now what we call displacement, or we call it amplitude. If that distance is maximum, we call it amplitude. So now, just before you release it, the velocity is zero, like this, and once it releases it, the velocity starts increasing. At this mean point, this middle point, the velocity become maximum. Rather, at this midpoint, the velocity is maximum, and it goes and the spring compresses and comes back to either this place, and at this point also the velocity is zero also, and it goes like this to and fro. Now, at this point we know that the velocity is maximum, which is just um a amplitude from when released. When I release it, it's just one amplitude. So we can use amplitude to calculate what we want to get, or we just use our normal logic. Remember, I said one cycle is from this place to this place back to this place. Maybe I should use another ink. I said one cycle or one oscillation is when I release this object, it moves to this point and it moves back. That is to and fro. That is one cycle. Now, for this one now, it is moving. It reaches here at first. Now, reaching here is just, this is the full cycle. This is the first amplitude, second amplitude, third amplitude, fourth amplitude. That's why one oscillation or one cycle is 4 amplitude. Now, moving like this, you just covered only just quarter. This is 1 2 3 4, just cover only just 1/4 of the cycle. That is when the velocity is maximum. And also, when it goes like this, that is half. It's when it is coming back also, it reaches maximum point. That is also 3/4 of the cycle. So at these 2 points, the velocity are maximum. But in the option, we have 1/4. So the answer is 1/4 of the cycle where the velocity is maximum. Hope you understand. This next question, they said if the shock absorbers in a car go bad, then the car will oscillate at the least provocation, such as when going over bumps in the road after stopping. Calculate the frequency and period of this oscillation for such a car if the car's mass, including its load, is 900 kg and the force constant K of the suspension system is this. Now, here we are going to list all our parameters as usual. So listing all our parameters now, I have they say we should look for frequency and they say we should look for period. Now, the frequency they say we should look for, we don't know, and the period also we don't know. This gave us the mass of the car and including the loads, mass of everything altogether is 900. Then I have my mass to be 900 kg. Now this gave us the force constant. The force constant to be this. Then force constant K equals to 6.53 times 10 raised to power 4 nano Newton per meter. Now, if you want to calculate this one, the formula for frequency is 1 over 2 pi square root of K over M. All right. Now, 1 over 2 pi, you have your K to be 6.53 times 10 raised to power 4 all over, and you have your mass to be 900. And mind you can see that now mass is in kg, so I don't have to convert, and this is in Newton per meter, I don't have to convert also. Then I can just punch this into calculator directly. You will get 1.356 hertz. Then that is your frequency. And the second question says we should look for our period. And we know that our period is 1 over frequency. You can use this formula also, 2 pi raised square root of m over k, but this will go a long way. Since we have calculated our frequency, we can just input our formula inside that place. So our t equals to, our period equals to 1 over 1.356, and if you should calculate that also, we are going to get 0.74, approximately 0.74 seconds, and that's that for this question. Okay, for this question, they said, how much will a spring that has a force constant of 40 Newton per meter be stretched by an object with a mass of 0.5 kilogram when hung motionlessly from the spring? Now, we have a spring. Let me just draw it here. We have a spring attached to an object like this. Now we can calculate by just listing out our parameters. We were given K force constant, which is equals to 40 Newton per meter. We were given mass, which is equals to 0.5 kilogram, and we were given, okay, that's all. We were told to look for how much will a spring be stretched, which means we are looking for our X, or we call it our amplitude A, because that will be the total stretch, because it will stretch it downward. And we know that our force equals to negative kx. That is just the formula. And here we have A, but this A now, you can see that we are hanging it vertically, not horizontally. With like this, it's not like this, it is vertically. This vertically now, the force that will be responsible here will be the force gravity, the gravitational force, the weight of these objects will be the force that will drag this thing downward. So here we can now say that our A is mg, which is equals to minus kx, and we know that our g is constant, which is 9.8 meter per second square. All right, now we can compute. Okay, we are looking for our x, so we can say our x equals to mg over negative k, or mg over k. The negative sign is just telling you the direction at which it's moved, that it's moving in opposite direction. Now mass is 0.5 times 9.8 over our k is 40, and if you should punch this inside calculator, 0.5 times 9.8 divided by 40, you will get 0.1225 meter. Now it is being stretched by 0.1225 meter. And what does that mean? It means that if the spring is literally here before hanging any mass to it, and when we hang it, it moves from here to this point, which is 0.1225. That's just what it means. So we have found our distance or displacement, which yeah, we have found our displacement. Now question B says that calculate the decrease in potential energy goes into the spring. Calculate the energy stored in the spring by stretched and compare it with the gravitational potential energy. Now let's take it one after the other. Calculate the decrease in gravitational potential energy, and you can see that there will be a decrease because the potential energy, gravitational potential energy, is actually mgh. We will know that, which means it increase with increase in height and decrease in height. And we know that the height here is higher than here with respect to the ground. Gravity acts and pulls every object towards the ground, so we relate everything with the ground. So this place is higher than this place at the ground. So at this level, gravitational potential energy is higher than at this level. So if this is the final gravitational potential energy, then this object decrease in gravitational potential energy. Now let's calculate that. We have our gravitational potential energy to be mgh. Now our mass is being given to us, which is 0.5. Our gravity, we know that it is 9.8, and our height is this distance that it moves. It's moved from here to here. Then we can say that is 0.1225. That is the change in distance. And even if I should input the negative sign, you will see that it will give us negative answer. And we should multiply everything here together, punch it inside the calculator, we will get approximately 0.6 joules, and that is the gravitational potential energy. Now the second question says we should calculate the energy stored in spring by this stretch. Now energy will be stored in this spring, and the energy stored in spring is half kx squared. As we discussed earlier, the energy stored in this spring is half kx squared. Total energy is equals to potential energy plus kinetic energy, and we know that our total energy is half ka squared. So we can, and I said this can also be a, because that is the maximum displacement it gives it. So we can say that our total energy is 1/2, our k is 40, and our amplitude is 0.1225 all squared. If we should put that one also in calculator, we will get our total energy to be 0.3, approximately 0.3 joules. And they said we should compare compare it with gravitational potential energy, and where does the rest of the energy go. We can see that we have 0.3 and we have 0.6. The total energy ought to be 0.6 because this is the potential energy that it lost. So since that is the energy that it lost, then the energy loss should be equal to the energy gained by the spring. The total energy gained by the spring. So the total energy gained by the spring is now 0.03. So where did it go? Remember what they said here, that when hung motionless, which means we are the one that hang it, and we don't, if you should hang it, it will fall and it start damping, it start moving up and down, and then it stops at this equilibrium. But they said motionless. Since motionless, we are placing it carefully and we are supporting it with our hand, which means the one that ought to go to the kinetic energy is actually in our hand. The rest of the energy is the one I can say is due to the heat generated with our hand, because it's the one that our hand produce. Is our hand that actually cause the object not to oscillate. So our hand eliminated this half k v square away from this spring. That's why this and this are not equal. A suspension bridge oscillates with an effective force constant of 1 times 10 raised to power 8 Newton per meter, how much energy is needed to make it oscillate with an amplitude of 0.1 meter if soldiers march across the bridge with a cadence equals to the bridge's natural frequency and impacts 1 times 10 raised to power 4 joules of energy each second? How long does it take for the bridge's oscillation to go from D 0.1 to 0.5 amplitude? If you can try it, you can just pause the video and give it a try. Let's first write out our parameters. The suspension bridge oscillates with an effective force constant. Now, we were given force constant. We were given force constant to be 1 point. So we can write it here. K equals to 1 times 10 raised to power 8 Newton per meter. So we were now told to find the energy. So we are looking for our energy. How much energy is needed to oscillate it with an amplitude of 0.1? Now, an amplitude is 0.1 meter. And don't forget that our total energy is equals to half Ka square. Now, so we just impute our value and then we will get what we want to get, 0.1 all squared. If we should punch this inside calculator, we should get 5 times 10 raised to power 5 joules. All right. Now, for the second question, they said if soldiers march across the bridge with a cadence equals to the bridge natural frequency and impact this. Now, the soldiers are the one impacting their energy, the energy which is 1 times 10 raised to power 4 joules on this bridge each second per second. Let me just put it, let me say in 1 second. Okay, how long does it take for the bridge's oscillation to go? So we are looking for time it will take the bridge if it goes from 0.1 to 0.5. Now, at 0.1, we have known the energy. Then we look for the energy at 0.5. Then we subtract. Then after subtracting, we can now divide it by this. Now, let's take it one after the other. We have looked for the energy at 0.1, then energy at final energy. Let me put that. So this will become our initial energy because this will be the initial point because it is moving from this point to this point. Then this will be our initial point, which is our initial energy, and this will be our final energy. Okay. Now our final energy is also the same thing, half Ka square, but our K in this case is now our A in this case is now 0.5 squared, and by the time you put inside calculator, you should get 1.25 times 10 raised to power 7 joules. Okay, now since we've got that to be our final energy, then we are going to find the change in energy. Now the change in energy is just the final energy minus initial energy, and by the time you subtract our final energy, which is 1.25 times 10 raised to power 7 minus 5 times 10 raised to power 5, by the time you subtract it from each other, we get 1.2 times 10 raised to power 7 joules. Now, this is the energy that we take them to move it from that point to that point. Now, the energy they are using is now this per second. So, how long will it take them to now? How long will it take them for the bridge to move from that point to that point? So they need this total energy. Then we can say, okay, in 1 second, they use 1 times 10 raised to power 4. Then in how many seconds? Let me use T for it. In how many seconds will they oscillate the bridge by 1 times 10 raised to 1.2 times 10 raised to power 7? Then we cross multiply, and by the time we cross multiply, we have 1 times 10 raised to power 4t equals to 1.2 times 10 raised to power 7 second, and we divide both sides by 1 times 10 raised to the power 4, 1 times 10 raised to the power 4, and by the time we do that, we have our time to be 1200 seconds. And if they want it in minutes, then you divide this by 60, and if you divide this by 60, that is actually 20 minutes. That is how long it will take them. It means if they are still marching on that bridge for 20 seconds, the bridge will will oscillate from this 0.1 to this 0.5. If a car has a suspension system with a force constant of 5 times 10 raised to the power 4 Newton per meter, how much energy must the car's shocks remove to dampen an oscillation starting with a maximum displacement of 0.0750? Now, here we are to list our parameters out. So the first parameters that we have is the force constant, and the force constant is K, which is 5 times 10 raised to the power 4 Newton per meter. And they said how much energy, then we are looking for our energy, which is what we are looking for. Must the car shocks remove the damping oscillation starting with maximum displacement? We were given maximum displacement also, which is our amplitude, 0.075 meter. Then we know that our energy is equals to half Ka squared, and this is pretty easy, which is half 5 times 10 raised to the power 4, and our A is 0.075 all squared. Then if you punch this inside calculator, we should get 140.625 joules, and that's about the question. This is another question. How much energy must the shock absorber of a 1200 kg car dissipate in order to damp a bounce that initially has a velocity of 0.8 meter per second at the equilibrium position? Assume the car returns to its original vertical position. Now, let's list out the parameters. They said how much energy, then we are looking for the energy that shock absorber that have this mass, M equals to 1200 kilogram, dissipate in order to damp a bounce that initially has a velocity. Now note this place very well. They said it initially has a velocity of 0.8 at equilibrium position, and remember what I said about the equilibrium position. At equilibrium position, velocity is maximum, so we were given our Vmax, which is equals to 0.8 meter per second. Then assuming it returns to its vertical position, so how much energy? Now the energy here is the total energy, as we know, and the total energy at the equilibrium position, remember when we talked about our video, we said at the amplitude, at the maximum amplitude, our total energy is equals to our potential energy. At the main position, our total energy is equals to our kinetic energy, and at the amplitude also, like at the negative side of the amplitude, our total energy is also equal to our potential energy. If you don't understand, or if you haven't watched our video on how we derive formula and explain this, you can go back and make justice to that. And then here that we are talking about the equilibrium position, you know that the total energy will be equals to the potential kinetic energy, which is half mv square, and our mass was given, our velocity also was given, so we can just plug in our answer, which is 1200, and our velocity 0.8 all squared. And then by the time we punch this inside calculator, we will get 384 joules, and that's that for this question. Okay, now let's solve this question. If you can solve this question, you can pause it and give it a try. When a family of 4 with a total mass of 200 kg step into their car in their 1200 kg car, the car's spring compresses 3.0 centimeter. What is the spring constant of the car spring, assuming they act as a single spring? How far will the car be lower if loaded with 300 kg rather than 200 kg? Alright, now the first thing is to list all our parameters out, and the mass given to us is 200 kg. Now, don't go ahead and add this and this together. The reason is that you have a car, and the car has a shock absorber which has a spring. Now, you step in the car and the car compresses this. Remember, your car is on that spring before. This 1200 kg car is on that spring before, so it doesn't really count. When you step into it, that was when it can compress to this, not that when they added the car weight and your own weight. Hope you get this. So what happened is that when this car is on that spring before and they did not consider that spring extension when they have installed the car, like the complete body of the car. Now, you stepping in the car compresses this far. So the mass you are checking is only the mass, your mass, and the mass and the distance you are checking is that 3 centimeter. So don't go and add this and then this 200 and this 1200 kilogram. Don't go and add them together. And they say you should look for the spring constant. Now, we all know that for us to talk about something moving directly downward, there must be a weight. Like a weight is what makes something comes down without, if you are not applying any force, and we are talking about mass in direction of gravitational force, so it's your weight that compresses it, which is the force that we will consider. Now, your acceleration due to gravity is 9.8 meter per second square. So we know that force is equals to negative kx, and we know that your force is ma equals to negative kx. And for this mass, we said it is acceleration due to gravity. For this acceleration, we said it is acceleration due to gravity. So that is mg equals to negative kx. Then we can now plug in our question. Okay, we are looking for our swing constant, so we can say our k is equals to negative mg over x. Then let's plug in our question. That's 200 times 9.8 divided by x, which is our, now this is in centimeter, we have to convert it to meter, which is 0.03 meter. So that is 0.03. Then your spin constant will be 65333 Newton per meter, or we say it is 6.53 times 10 raised to power 4. So this is our spring constant. Then the second question, they said how far will the spring be, will the car be loaded with 300 kg rather than 200 kg. Now our new mass is now 300, no 300, and our k remains the same, 6.33 times 10 raised to 6.53 times 10 raised to power 4 Newton per meter. And our x is what we are looking for. Our acceleration due to gravity is still 9.8 meter per second square. Now, using the same formula, mg equals to negative kx. Then we are looking for x in this format, so we say x equals to mg over k. X will now be equals to, m is 300 times 0.9, times 9.8 all over 6.53 times 10 raised to power 4, and our x will be 0.045, and we should convert this to a meter. This is a meter. If you want to convert it to centimeter, you divide this by 100, then that will be 4.5 centimeter. And we can see when higher mass enters the car compresses more. Now the next question, a sperm of mass 0.3 gram, weight in its web of negligible mass. A slight movement causes the web to vibrate with a frequency of about 15 Hz. Estimate the value of the spring stiffness constant for the web. At what frequency would you expect the web to vibrate if an insect of mass 0.1 gram were trapped in addition to the spider? Now, if we want to solve this type of question, we list out our parameters since we have understood what is going on in it. So we were given mass to be 0.3 gram, which we convert to kilogram, and converting to kilogram we divide by 1000. That will give you 0.0003 kilogram. Now, they said a slight movement caused the web to vibrate at a frequency. We were given frequency of 15 Hz. Now, estimate the value of the spring constant. So we are looking for our K. That's the first question. Now, remember that we are given frequency and we have mass. What are we going to do? Remember the formula for frequency, which is equals to 1 over 2 pi square root of K over M. Now, F equals to 1 over 2 pi. Our K is what we are looking for. And we have our mass to be 0.0003. Now I can just change this force to what was given, which is 15 frequency rather to what was given to, which is 15 Hz, and then I can, if I cross multiply, I will have 15 multiplying 2 pi, which is equals to square root of K over 0.0003. Now 15 times 2 pi is 94.248, which is equals to square root of K over 0.0003. Then the next thing is to square both sides. If you square both sides, you will have 94.248 squared, which is equals to, if you square this one, square root will get cancelled out, all squared. Square will cancel square root, and punching this into calculator, you will have 8882.644, which is equals to K over 0.0003. By the time you cross multiply, you will have your spring constant to be 2.6665 Newton per meter. Now that is your spring constant, 2.665 Newton per meter, or you can approximate to 2.7. Now the second question says that at what frequency would you expect the web to vibrate if an insect these were trapped addition to the spider? Now we have added another mass to it, which means the new mass will be the mass of the spider, which is 0.3, plus the mass of the insect 0.1, which will give you total of 0.4 gram. Converting this to kilogram, you have 0.0004 kilogram. You divide by 1000, and then you say you are looking for the frequency. Remember that your frequency is 1 over 2 pi square root of K over M. Then you can just plug in your value. 1 over 2 pi square root of K is 2.665. Mass is 0.0004. And by the time you punch all this into calculator, you will have 12.99 Hz, and that will be your final frequency. Okay, this is the next question. A 2 kilogram mass hangs at the end of a spring whose constant is this. Whose spring constant is this? The mass is displaced by a distance of this and release. What's the maximum velocity? All right, and we know that if we are looking for okay, we list out our parameters first. The mass given to us is 2 kilogram, and the spring constant K is 500 Newton per meter, and they said it is being displayed at a distance of this, which means the amplitude is 10 centimeter. And mind it is being displayed by this distance means they stretch it to that amplitude before it was being released, and that is this distance given to us. What is now the maximum velocity? Remember, we derived formula in our last video that the velocity, the maximum velocity is equals to omega A. when we say that v equals to omega square root of a square minus x squared, and we say that velocity x, the displacement will be 0 because at mean point velocity is maximum. Then if it is 0, then this become only amplitude, and square root of amplitude is still amplitude. Square root of amplitude square will give you omega a, which is this. But remember that omega square is equals to k over m, and omega will be equals to square root of k over m. If I should replace this with this, because what was given was m and k, not given omega, then we can say that my velocity v max is equals to amplitude times omega square root of k over m. And if I should plug in my value, remember this should be converted into meter, which is divided by 100, which is 0.1, and that is 0.01, sorry, 0.1, which is 0.1, and plugging it inside this, we have 0.1 square root of our constant is 500 and our mass is 2. This divided by this, that is 250, that is 0.1 square root of 250, and we should punch this inside calculator. You should have 1.58 meter per second, and that is your velocity, the velocity max. That is the maximum velocity that this spring has. Let's move to the next question. Okay, this question is like the one that we just finished solving. If you can try it, just pause the video and try it. So we have a frictionless system. Okay, a frictionless system has a 2 kilogram mass attached to a spring of force constant this. If the mass is displaced at the distance of this and release, calculate the frequency and the maximum acceleration. Now let's take it one after the other. List all your parameters. Mass equals to 2 kilogram. The spring constant, which is k, equals to 400 newton per meter, and your mass displaced. Remember, the mass displaced is the maximum displacement, which is your amplitude, that is 20 centimeter. Converting this, we have 0.2 kilometer, and calculate the frequency. The first thing said we should calculate frequency. And what is frequency? We were given this, then we know that frequency is 1 over 2 pi square root of k over m, and f equals to 1 over 2 pi square root of k is 400 and m is 2. And by the time you punch this into calculator, okay, this gives you 200, and by the time you punch this into calculator, you will have your frequency to be 2.25 hertz, and that's for our frequency. And question B says you should look for our maximum acceleration, and don't forget that our acceleration is minus omega a, minus omega square a. That's our maximum acceleration. So our maximum acceleration is minus omega square a. Please, if you haven't watched our video on this, go and watch it. So a acceleration max equals to omega is not given, and don't forget that our omega square is equals to k over m. So I can just replace the omega square with k over m. So I will just say I have k over m times a. And don't forget that the negative sign is just telling you that it's going in opposite direction. So a max is equals to, our k is 400, mass is 2, and our amplitude is 0.2. By the time you call this, you have your a max to be equals to 40 meter per second square, and that is that for this video, for this question. Okay, this next question. They said a load of 16 newton attached to a spring hanging vertically. All right, we have a spring like this, and is a mass is attached, a load is attached to it vertically, 60 newton. All right, stretches this spring 5 centimeter, which means when this was attached to it, it stretches this spring with this amount. So we know that our our displacement or our amplitude is 5 centimeter. So the spring is now placed horizontally on the table. So we now place it back on the table. Let's assume this is the table. and we place the spring on the table and stretch 10 centimeter, we now stretch this thing. Maybe this is the main position, we now stretch it for 10 centimeter. So that 10 centimeter is the amplitude relative to this. We have two systems like this. We have two types of system. So the amplitude of this is this. The one of this is the one of 10 centimeter. So we are now looking for the force that is required to stretch it that amount. Okay. Now the first thing we are going to do is to find the spring constant, because this will tell us the spring constant. Once it is being hung on this and it stretches it this far, we can know our spring constant. So from our spring constant, we can use it to determine our force that can be used to stretch it this way at this on this surface. Now for our spring constant, now we know that F equals to kx or negative kx, and we know our force is this 60 Newton. 60 equals to negative k, and an x is 5, which is 0.05 meter. 0.05 meter. Then we divide both sides, so our k is minus 60 over 0.05, and by the time you divide this, you have 1200 Newton per meter. Don't forget, once again, the minus is just telling you the direction, so it doesn't really count in this question. Now for the second one, now we have known our spin constant. Then we can use our spin constant to determine the force that we use to stretch this object this far. Then we can say, okay, we have our force to be equals to kx again, our force, which is equals to our spin constant, times the maximum displacement, which is the amplitude, which is going to be 0.1 in this case. So the force will be 0.1 times 1200, which is equals to 120 Newton. So that is the force that is required to stretch that object that way, because of the spring constant is very, very high. So you can actually use one formula again. We are comparing two things together. We have force equals to negative kx. We can just say that negative f over x equals to k. And we were told in earlier this video that this constant can be duplicated with this as minus f1 over x2, x1 equals to minus f2 over x2. Minus can just get rid of them because we don't need it here. Now we have the first force to be 60 over the first displacement, which is 0.05, which is equals to the second force rather is what we are looking for, and the second displacement is 0.1. And by the time you cross multiply, you have f2 equals to 60 times 0.1 over 0.5 is 0.05. By the time you punch this inside your calculator, you will get 120 Newton, which was what we formerly got. So you can either use this or you go manually like this. Okay, this is the next question. They said the catapult consists of light leather cup containing a stone which is pulled back against two rubber bands. It takes a force of this to stretch the rubber band like this. What is the potential energy stored in the band when 50 grams of stone is placed in the cup and pulled back to this amplitude from equilibrium position? Okay, now the first thing we are doing is to list our parameters, and the parameters we have here is our first force, which is equals to 30 Newton, and our distance, which is 1 centimeter, which is equivalent to 0.01 meter. So we are told to look for the potential energy. Now the first thing we are doing is to find our spring constant, or our rubber constant in this case, which is the force constant. Let me just put like that, our force constant, which is equals to F equals to kx, and our F is 30, and our K is what we are looking for, which is and our X is 0.01. So we divide both sides by 0.01, and our K is going to be 3000 Newton per meter. Now since we have got our
K. Then we move to the question. They said, what is the potential stored in the band? So we are looking for the potential energy which is stored in the band. When a 50 gram, now we have a mass of 50 gram, which is equals to 0.05 kilogram, is placed in the cup and pulled back at our amplitude, because that is the maximum distance that was being pulled back from the equilibrium position. Now, we know that our potential energy is equals to half kx squared. But mind you, it has been pulled back to the end point. Just before we release it, our potential energy is equals to our total energy, which is equals to half Ka squared.
Compute the formula. We have potential energy equals to half K is 3000 and amplitude is 0.3. You can see the 0.3 in this case, and then we square it. By the time you punch this inside calculator, you get our potential energy stored in the band to be equals to 135 joules. 135 joules. Now, the next question says that with what speed does it leave the catapult? And we know that it will leave the catapult with maximum speed. And Vmax can be calculated in two ways. Now, the first way is to use omega A, since we know that at the main point, our x is 0, the displacement is 0, then our maximum velocity will be omega A. Then, if you should compute this one, our omega is square root of k over m times A. And then our velocity, maximum velocity will be equals to, our k is 3000, our m, the mass, is 0.05 times our amplitude is 0.3. If you should punch this inside calculator, we will get 73.48 meter per second. Now it will leave the catapult with this maximum velocity. But if you want to use the second formula, all right, we can, you know that the potential energy stored in the rubber is the total energy saved by the system, because at this point the rubber has not moved, and we said at the amplitude, at the maximum displacement, the total energy is equal to potential energy. Now, for total energy to be equal to potential energy, and we know that we are looking for the maximum velocity, which means our kinetic energy also must be maximum. Hope you understand. Like, the total energy stored in the rubber is the potential energy of this maximum, and from this we can see that this is the maximum energy. So if you now put this potential energy in place of total energy, we can now say, okay, our 135 must be equals to our kinetic energy, because energy is used to catapult must be the energy is used to move. Now the kinetic energy is half mv squared, which is equals to 135, and our m, which is mass, is 0.05 v square equals to 135. V square will be equals to 2, we multiply 135 because we cross multiply 2 times 135, and we divide by 0.05. Then what will be our answer now? So our v square will be equals to 5400. By the time you now take the square root of both sides, square root of 5400, our v will be 73.48 meter per second. And we can see that it is the same thing with this one. So any way you want to use to solve it, just know the logic behind it. This is the last question. It says that a spring stretches 0.15 meter when this mass is gently suspended from it vertically. Now, if you take this thing one after the other, the spring is suspended vertically like this. All right. Now, they said when this object, which is 0.3 kilogram, was suspended on it, it stretches to this extent, 0.15, which means from this now we can know our spring constant. That is for the first statement. Now, The spring is then set horizontally. That is another thing. Let's find our spring constant first. The mass given to us 0.3 kg, and our amplitude, which is our x, is equals to 0.15 meter. Now, the spring constant k is what we are looking for, and don't forget that when we hang this thing, the only force that is responsible here is the force due to gravity. It is pulling it down. Then our gravitational, the g will be equals to 9.8 meter per second. So we know that F equals to kx, or negative kx, and F is mg equals to our kx, and m is 0.3, our g is 9.8, u equals to k. I'm multiplying by 0.15, and if you should punch this inside calculator over 0.15, you get your constant to be 19.6 Newton per meter. Now that we have found our k, let's continue with the question. The question then say that the spring is set up horizontally. So the spring is then set up horizontally. So it moves this way. Let's assume it is being set up like this. The spring is being set up like this, right, with that same mass 0.3. And remember that since we have slanted it and we put it on a frictionless table, it means that the force on this guy is not gravitational force again. Now the mass is pulled, that the spring is stretched 0.1 meter from the equilibrium position. Now it is being pulled like this. Remember, it's not pulled downward because it's not gravitational force that we are talking about. So we are talking about the applied force here, which is being pulled like this. So since it is being pulled like this, the maximum amplitude that they said it gives it was 0.1. So we have our amplitude to be 0.1 meter now, and we have known our spring constant. Our mass also is 0.3 kilogram. All right, now the first one, we should determine our spring constant, which we have determined that from first. The second thing is, what's the amplitude of the horizontal oscillation? This is the horizontal oscillation. The amplitude is 0.1 because they said it is being dragged this distance, so the amplitude is this horizontal oscillation. Now the next one is the magnitude of the maximum velocity. We know that the maximum velocity is equals to omega a, and omega is square root of k over m times a. Now we can now plug in our value. We have 19.6 over our m is 0.3 multiplying by our amplitude 0.1. So the velocity is now equals to 0.81 meter per second. So this is the velocity, maximum velocity at which it moved. Then the next question says, find the magnitude of the velocity when the mass is 0.05 meter from the equilibrium position, which means our x now given to us, okay, this is our b, our c, our x given to us is now 0.05, and we know that velocity at any point is omega square root of a squared minus x squared, and we know our a to be 0.1 already and our x to be this. Then we say that our velocity equals to omega, which is our square root of k over m, multiplying square root of a squared minus x squared. I can multiply these two together, having square root of k over m into brackets a squared minus x squared. I can just put it like this. All right, now what is our k? Our k is 19.6. Our a is 0.1 all squared minus our x is 0.05 all squared, and we are dividing by our mass, which is 0.3. Then our final velocity will be 0.7 meter per second. So that is our velocity at that point, and we can see it is not even up to the maximum velocity. Yeah. Now the next question says the magnitude of the maximum acceleration of the oscillation. Now to find the maximum acceleration, we know that our a max equals to
omega square A, and our omega squared is actually K over M times A. Then if you should plug in our value, we have our maximum acceleration to be equals to, our K is 19.6 over 0.3 multiplying by our amplitude, which is 0.1, and our A max will be equals to 6.53 meter per second square. That's our maximum acceleration. Now, to the last one, we said we should look for our total energy. Okay, find our total energy. Now, the total energy now, we know that the formula for total energy is half Ka square. All right, now the total energy will be equals to half, our K is 19.6 and our A is 0.1 all squared. Now, the total energy that we are going to have is going to be 0.098 joules. Then we move to the next one. The next one says that find the kinetic energy and potential energy at half amplitude. Now, we are not looking for the maximum kinetic, we are not looking for the maximum potential energy. We are looking for both of them at half amplitude, which means our x will be A over 2. So the distance we are considering is half of a amplitude, and amplitude is 0.1, and divided by 2 we have our x to be 0.05 meter. Then we can now find our kinetic energy and potential energy. Now, finding our kinetic energy, first we have one formula for our kinetic energy, which is half K A squared minus x squared. Remember, it is half mv squared, and v is omega square root of A squared minus x squared. By the time you represent this inside this, you have half m omega square will become omega square will become omega square, and square will cancel square, which will give you A square minus x squared, and m omega square is our K. So that's why we have this there. So it can also be written in this format, which is half K A square minus x square. Then we can now say that our kinetic energy is equals to half, our K is 19.6, our amplitude 0.1 squared minus our displacement 0.015 squared. So our kinetic energy, if you compute this inside calculator, we have 0.0735 joules. That's our kinetic energy. Now let's find our potential energy. Our potential energy, we can actually subtract this from our total energy to get our potential energy. But if you don't want to do that, you can go manually, which is half K x squared, and we know our x to be our K to be 19.6 and our x is 0.05 all squared. And if you punch this inside calculator, you will have 0.0245 joules. And by the time you add, that's our potential energy. If you now add this and this together, you must get this 0.98. And let's try that, and you will see that that is what you are going to arrive at. And that is that about the questions on mass spring system. If you have any question, you can put inside your comments, like, subscribe, and share. Thank you.